Okay. It is my great pleasure to introduce our first keynote speaker for this morning, Professor Pennung Warnitchai. He is professor and chair of the Structural Engineering program at the Asian Institute of Technology, AIT, and also founding director of the Earthquake Research Center of Thailand, EARTH. We have a doctorate from the University of Tokyo and well over 3 decades of experience in academia and research. He is thus a leading voice in earthquake engineering, structural dynamics, and plays a vital role in advancing infrastructure safety and disaster resilience in Southeast Asia. Professor Pennung has been instrumental in the development of Thailand's seismic safety framework and has served on numerous expert committees tasked with formulating national building codes and disaster risk reduction policies. His expertise is therefore often and frequently sought after by government bodies, for example, most recently, into a national investigation into the major building collapse in Bangkok that happened as a result of the earthquake back in March. Today, he brings us valuable insights into how the stability of our physical infrastructure underpins the reliability of our digital world. Without further ado, please join me in welcoming to the stage Professor Pennung Warnitchai.
Hello. First of all, I'd like to thank the organizer for inviting me here. I feel a little bit worried that because my background is structural engineer, and I think it's quite different from you, who are the internet and IT experts. But I will try to make the story as clear as possible, although it may be coming from the viewpoint of structural engineer. So the title given to me is this one, the Bangkok earthquake and what we learned from it. Let me begin by showing this slide. On the right hand side, you can see many red dots. These are, each dot represent one earthquake event. So this picture show the seismic activity over 100 years approximately in this region. So you can see we have so many earthquakes, but most of them are in Myanmar, in southern part of China, in Andaman Sea. But we have some in Thailand as well, in the northern part, the western part, but none of them are in Bangkok. Okay, these are the location of earthquakes. On the left-hand side, you can see, what I want to say is all these earthquakes are tectonic earthquakes. It means that all these earthquakes are created by the movement of tectonic plates. And the left-hand side shows the active fault, which is where the tectonic plate move. And you can see there are many different colors. The red one show very high rate of seismic activity. The green lower and the gray are much lower. In this region, you can see one long active fault that is called Sakai Fault. Is in center of Myanmar, passing through many cities, Mandalay, Naypyidaw, Paco, and pass close to Yangon and go down to the sea. So this is one of the most dangerous active fault in this region. And if we compare with many other active fault around the world, this one ranked in the top 3 of in the world level. So this is the present condition that about the earthquake. Now, as most of you know, on 28 March this year, we had a large earthquake happening along the Sakai Fault. Okay, it started at around the Mandalay location, near the city Mandalay of Myanmar. But it was created by the slip, or in engineering we call the rupture. It's a kind of the slip movement. One side go the north, one side go to the south. So this slip along the fault, starting from Mandalay down to Naypyidaw. Okay, more than 300-400 kilometers long. So you can see the red zone. Along this red zone, the ground shaking was extremely strong. And as you can expect, many buildings collapsed, many buildings damaged, a large number of casualties, mostly concentrated along the red zone, the yellow zone. But what surprised most of us is the impact of this earthquake then spread as far as Bangkok, about 1,000 kilometers from the epicenter, which is in Mandalay. So we can come down to Bangkok. I think I just collect this from social media. I think many of you have a direct experience from this earthquake, so you can you also have a story to tell. This is a water spill from the swimming pool on the top of tall buildings. Tall buildings sway, form.
ผมไม่ทำไมนั่งหัวเป็นหมุนนู่น
Train and transit system. And the highlight was the this-story building collapsed by the impact of the Okay, I think that gives you some background about what was happening during that day. But but it was not the first time that we had this impact from distant earthquake. What I want to say is 28 March event was the strongest that we have ever experienced in Bangkok. But when we look to the past, we found that there were many other events, not as strong as the recent one, but it showed that large earthquake from very far distance can actually give an impact to tall buildings in Bangkok. So my research team have been working on this problem for more than 20 years. And we found that one of the key factors was the presence of soft soil basin in Bangkok. If you ask any earthquake engineers, they can tell you that the soft soil condition can lead to the stronger ground shaking. The soil basin can amplify the ground shaking effect. Okay, and if you look at the whole country, the green zone show rather stiff and hard soil. The yellow orange zone shows softer, and the dark red is extremely soft. So Bangkok, the capital city, is located in the soft zone, a soft soil basin. Okay, and this basin actually is quite deep, and it has an ability to amplify the ground shaking. Let me show you some example in the past. Many years ago, we had a 6.8 magnitude earthquake in the north of Thailand, in the borderline between Thailand and Myanmar. And we record the ground motion, one on the hard soil, Surin province, another one in Bangkok on the soft soil basin. If you compare them, the ground motion record in Surin is much lower in magnitude, in intensity compared to that in Bangkok. And from this, we can calculate the impact of ground shaking to buildings in Bangkok and in Surin. So we convert the ground motion into the calculation of impact to the building. So you can see, let me explain this graph to you so that you can have some idea about the impact. The vertical axis shows spectral acceleration is just one type of index which is index of the impact to the building. Earthquake induced force in the building will be increasing or decreasing proportional to spectral acceleration. So if the graph is high, mean it produces higher impact to the building. And horizontal axis show the natural period, which means that each building has its own vibration period, we call natural period. But roughly, for 10-story building, natural period will be about 1 second. 20-story building, natural period will be about 2 seconds. 30-story building, about 3 seconds, approximately. This is just to give you some rough idea. And what you can see here is buildings in Bangkok will have much more earthquake effect compared to those in Surin. Okay, because the amplification effect of the soil basin. And another point that we can see from this graph is the buildings that relatively have longer period, 1 second, 2 seconds, 3 seconds will have more impact than building with shorter period. So let me try to explain this point. I try to make it simple. So this animation I asked my student to make. You can see 3 different buildings here. The tall one represents a kind of 50-story building with natural period about 5 seconds. The middle one, it represents a 25-story building with natural period about 2.4 seconds. And the small one represents a kind of 10-story building with natural period around 1.1 second. If the ground moves slowly, at the vibration, the ground motion period about 5 seconds, is going to shake the long period structure, the tall one, because there is a matching between the ground movement and the vibration period of the structure. This is called resonance effect. Now, if we change the way the ground moves, make it move faster at a shorter period, 2.4, it's going to produce more impact to the middle one that have a natural period matching with the ground motion period. And if if the ground moves at a shorter period, high frequency is going to shake the small one. So for the case of Bangkok, I think we are closer to the first case and second case, but not the third one. In fact, the ground motion will be a mix of many frequencies, many periods. So it will excite not just 1 or 2, but many that match with the frequency inside the ground motion. But the issue is different basin will amplify different vibration period, the ground motion period. Osaka basin may amplify about 6 to 2 second vibration period. Taipei basin about 2 seconds. Kathmandu basin about 5 seconds. Now what about Bangkok basin? So because of this question, our team spent many years in investigating the Bangkok basin. We spent many years applying the technique called array microtremor measurement. We conduct a survey at many locations inside this large basin. And we obtain the dynamic properties of the soil basin. And we also know the basic geometry of the soil basin. This helps us to make a model about soil basin, and we can predict is amplification characteristic. We can determine what type of vibration period it will amplify, how strong it will amplify. Okay, I think this picture just show you some simple idea about the depth to the bedrock. For Bangkok is located at the center of the basin, and the depth to the bedrock is around 800 meters. So we are in the deepest zone of the basin. So after knowing the property of the basin, and we combine with seismic hazard assessment, consider all the possible earthquake source, the distance from the source, and everything, we came up with a conclusion that Bangkok and surrounding province are at risk of disaster from distant large earthquake. I made this slide many years before the event in 28 March, and it's still true. Okay, we came up with a conclusion that the city lies on a large and deep soil basin, which can strongly amplify long period ground motion. And a large number of high-rise buildings with long natural period will strongly shaken by the resonance effect with this amplified ground motion. Our team also predict that there are 3 possible earthquake scenarios that are quite dangerous for tall buildings. The first one is earthquake of magnitude 7 to 7.5 in Kanchanaburi province, which is around 200 kilometers western in the western part of Thailand. And the second one is the earthquake of magnitude around 8 at the Sagaing Fall in Myanmar. The second scenario already happened on 28 March. And the third one, earthquake of magnitude around 8.5 to 9 at the Arakan subduction zone, which is on the western part of Myanmar. So all these 3 are quite dangerous for tall buildings in Bangkok. And when we predict this, we also say that all these 3 are not easy to happen. The chance that it will happen during our lifetime may be less than 10%. The chance that it will not happen during our lifetime is more than 90%. But probably we are wrong. It just happened. After making this calculation, we explained that, this is a rare event, but by some reason it's already happened. Of course, after knowing this, we have been preparing for such dangerous earthquake. We have a ministerial regulation that requires buildings to be designed and construct for earthquake resistance since 1997. And 10 years after that, in 2007, we expand the control area to cover Bangkok and surrounding province. Which means that since the year 2007, all tall buildings in Bangkok are required to be designed and construct for earthquake resistance. Okay, that's the way we prepare for the earthquake. And we also develop a kind of national standard for earth seismic resistant design for building and structure. Actually, this is a new version, but the first version was issued on 2009, and this is a revised version in 2019. And in this national standard, we actually divide the Bangkok basin into 10 different zones, and for different zones have a different design spectrum. Design spectrum is defining the level of earthquake impact to different building with different natural periods. Okay, so you can see a graph that 10 different curves for 10 different zones. So this is the best estimate before we have any earthquake. So this is based on only scientific information that we have. So Bangkok is in zone 5, and you can find the zone 5 curve on that. That is the way we tell our engineers that you should be prepared for earthquakes. You should design your buildings and structure for this level of earthquake intensity. And then it happened. On 28 March, the ground was shaken, and in Bangkok we have about 5 seismic stations available, and from this seismic station we have ground motion sensor, and we have a recorded ground motion time history available. So we can see how the ground move, how the shaking looks like. This is in the station in near Prachom Kao, Thonburi, KMUA University. And this is near Sirikit Convention Center. So we have about 4 or 5 stations available. The first thing we did after we obtained this record was to compare the ground motion record with what we put into our standard. So you can see here, this is the graph. The vertical axis again show the spectral acceleration, which is related to level of earthquake-induced force in the building. The horizontal axis still the natural period. You can see the red curve, and you can see the violet color curve. This represents the design basis earthquake, or we call DBE, and maximum considered earthquake we call MCE. This represents the maximum level of earthquake we expect to happen in Bangkok, and is have a very long return period, 2,000 years. The one that just happened on 28 March was the curve below in a color. It was not as high as DBE, it was not as high as MCE. But when you look at the long period range, it's somewhat comparable. And even for longer period range, in 6 seconds, it's slightly exceeding the level we estimate. Anyway, overall, we think that the ground motion that happened on that day, although it was the strongest ever experienced by most people here, strongest ever experienced by people in Bangkok and experienced by tall buildings, is still within the limit that we tell engineers to design the buildings for. So if they follow the regulation properly, we should not see any disaster. Okay, but it is possible that under such ground motion, there will be some damage to the structure. Okay, damage to non-structural component, or maybe damage to some not serious damage to structural element. That is what we expect when we compare with this standard. So this is a rough statistic I got it from Thailand Structural Engineering Association. They conduct many surveys by volunteer structural engineers, and they reported that around several hundreds of buildings have damage to non-structural components like non-structural masonry wall, partition walls, ceiling, damage to elevator, damage to many non-structural elements. So that is several hundred buildings. That actually, although not impact to the structure, it actually give a strong impact to functionality of the buildings. And we have just about 10 buildings that have damage to structural components, okay, especially the reinforced concrete wall, which are considered to be important component structural element of the structure. And one building collapse is a state auditor office, new building that completely collapsed. So that the collapse is beyond our expectation. So this shows you the idea of slight to moderate damage. I show you just only the damage to masonry wall, partition walls. So this is small level, slight to moderate level. But in some building, we can see more severe damage where you can see through, okay, to the other side, okay, the non-structural wall. Okay, this is not affecting the safety of the structure. But in less than 10 or around 10 buildings, we have this level of damage we call significant structural damage, where you can see the damage to structural wall. This is a reinforced concrete wall. The concrete crush and the reinforcement steel bar buckle. Okay, this is appeared to be quite dangerous. This is beyond what we expect. Okay, and the type of the failure actually is considered to be a brittle form of failure, which is quite dangerous because when this happens, it means that the structure cannot deform further. If it's subject to slightly more stronger shaking, it may lead to dangerous. It may lead to the collapse. So damage to structure is quite the main concern for structural engineers. And this is another one, tall buildings and damage to structural walls all around. Okay, but fortunately this one still standing, and some brave engineers are trying to repair and reinforce the structure. So when we compare with the damage reported elsewhere, I think we find more or less the same picture. Okay, this is in Chile, when it's subject to a strong earthquake. Many structure with shear wall, with a reinforced concrete wall also damaged in a similar pattern. Okay, I'm actually, we are actually trying to learn from this event. We are actually trying to collect many data from this event and then try to understand the impact of this event to many different buildings. So we trying to calculate one index that we think will be the best representative to the damage level. So we are trying to calculate the maximum roof top displacement of the structure we call roof drift, divided by the height of the building, delta by h, we call this roof drift ratio. We believe that the damage to the buildings, large or small, will be more or less proportional to this index, the roof drift ratio. So after using the ground motion available, we are able to calculate the roof drift ratio, and it come out to be like this. So we have the vertical axis show the roof drift ratio, horizontal axis show the natural period. Okay, let me give you some rough idea what does it mean. Again, natural period 1 mean about 10 story, 2 story, 20 story for 2 seconds. 30 story for 3 seconds. So most of the building in Bangkok, we have natural period somewhere between 1 to 5 seconds. Most of them. But there are a few super tall buildings, like Mahanakon, we have a natural period around 6 to 7 seconds. And some other super tall building may have a natural period around 7 to 8 seconds. But not many are in this range. Most of them are in this range, 1 to 5 seconds. And within that range, we have one outstanding peak. That is a peak of around 3 seconds. Okay. This means that the buildings around this natural period will have more, will vibrate stronger than other buildings. Okay. So we found that the hospital, we found the structural damage, Warnitchai Hospital, 25-story building, fall within this range of 3 seconds. We found that the Immigration Bureau office, which also have the damage to structural wall, also about 24-story high. There's another private building in Siam Square area, about 24-story building, also have suffered structural damage to the structural wall. And that may also include the State Auditor Office building, which is about 30 story. All of them just fall within the 3 second period. Okay. Somebody say that this earthquake event was a big test for tall building in Bangkok. I agree with the idea. It's a big test to check whether they can stand a strong earthquake or not. But the point is, the test is not the same for every building. Some buildings will be given stronger tests because the load to them are stronger. Okay, especially the buildings in 3 seconds will have stronger impact to their structural components. Now, but what I want to explain here, another point is that you see many graphs with different colors. All these different colors depends on another factor, which is normally not discussed, but is well known to structural engineer. It's called damping ratio. Damping ratio is energy dissipation ability of the building. I need to explain this a little bit so that you will understand, because this is related to the countermeasure I will explain in a later part of the story. So this is a damping ratio tells us about the ability of structure to be able to dissipate energy. These 3 buildings have identical size, identical height, have the same natural period. But if we shake them and let them freely vibrate, the one with high energy dissipation ability, we call damping ratio 5%, will stop first. The vibration for the those with 2.5% will continue to shake and stop later. The one with 1% damping will continue to shake more. Okay. In the past, we used to believe that our buildings have a damping ratio around 5%. But in a modern guidelines, new standard from the US suggests that we should consider damping ratio lower for tall building. So our new standard in Thailand, we follow the US and we set it to 2.5%. That was recommended from the US guideline. But this event, after we check many data, we have many recorded movement sensor on tall buildings. We analyze the movement of the tall building by using pixel tracking from video and many others, which I cannot explain, give you the details of that. But we came up with the conclusion that the damping of our tall building, many of them may be as low as 1%. Okay, so we used to believe that our building have a damping about 5%, but new standard suggests that 2.5. But what we found in the reality, maybe 1%. So why this point is important? Because if we again check these 3 buildings with different damping by the same ground motion, the one with 5% will not have high amplitude. The one with 2.5% will have higher amplitude. And the one with 1% will have highest amplitude. So this actually control the level of the impact of earthquake to tall building by this important parameter. So let's come back to the picture again. The blue curve is for damping of 1%. The red curve are for damping of 2.5%. And the green curve is for 5% damping. So some buildings may have high damping, some buildings may have low damping, but we think that many of them may have a damping of about 1%. So that leads to high roof drift ratio. Okay? But that is for the calculation from one ground motion. That ground motion is a station near Chatuchak area, near Bangkok Metropolitan Administration Office. And we can actually estimate the yellow zone is the level of roof drift that you can starting to see slight to moderate damage to your partition wall, non-structural wall. The orange zone is the level that you will find severe damage to your partition walls. We can estimate the impact to many other non-structural components, but I use partition wall just some idea. How about the structure? So we are talking about impact to non-structural component. If a structure is properly designed by making it ductile, making it well designed for earthquake resistance, I think we can go up to 2%. Not this level. This level is about 0.6, 0.7 maximum percent. But if we design a structure to be able to deform well, we call ductile system, we can go up to 2%. Okay? So we don't have to worry about this level of earthquake if we implement the proper seismic design. Now let me show you the calculation from other station. This is from Queen Sirikit National Convention Center. We still can see 3 seconds, but this is a north-south direction. This is east-west direction. We see also the peak in 4 and 5 seconds. So different locations have a different ground shaking characteristic, and that's because our basin have its property vary from location to location. So you will not know that this area it's going to produce a stronger effect at which period. So it's better to actually design for all possibility. So this is for Thonburi side. Now I come and this is a state auditor office, the one that collapsed. We also make some calculation. The reason for the collapse is still under investigation, which I cannot, I do not know yet, but I'm the member of investigation team. But initial analysis show that they are falling into the range near to the peak of 3 seconds. So it is possible to have stronger impact than many other buildings because there is natural period just for it to match with the peak effect, as you see in the graph. That is one of the key factors leading to the collapse, but there may be many other factors. So that is another story to tell later. Now, I come to the last part. So what do we have to do? Or what do we need to prepare for the future earthquake? I think as you can see here, this is a Sakai fault. The rupture is from Mandalay to Naypyidaw. The rupture does not go from the top to the bottom of the fault yet. The fault is about more than 1,000 kilometers long. It's just rupture only some part of that. In the future, it may continue to rupture from Naypyidaw to pass to Pak Ko, pass through Yangung and go down to the sea. So we have to see how much is a possibility of that. To understand that, we have to look at the history of earthquake rupture along this fault. So I put it, instead of north-south, I move it to horizontal fault. And this one show the time, and this line show the rupture zone. The recent one is a rupture between here to here, okay, from Mandalay to Naypyidaw. But the other horizontal line show the rupture in the past. In Mandalay, we have the rupture in 1956, 1912. In Naypyidaw, we have a previous rupture in 1839. So it's not happening easily. Okay? The past event in Mandalay was so many years ago. The past event in Naypyidaw zone was nearly 200 years ago. How about the possibility of rupture from Naypyidaw down, pass through Piu, Pak Ko, and Yangung? The past event were at around 1930. So it's about 90 years ago. So I'm not sure when it will happen. I cannot predict the future, but this is the past behavior history of the fault. I think it's quite a good chance that you will not see this level of earthquake again during your lifetime. But there is also a possibility that you may see it again as well. Okay? If it happened as this one, 1930, 7.3, 7.2, the impact to Bangkok may not be that strong. But if it's a long rupture, 7.7, like the one in 28 March, the impact will be stronger than what you experienced in 28 March, because it's become closer. So what to do? We may have this impact, but the next time it may not happen at the same pattern, because every earthquake, the peak of this, not depending on the basin amplification, is also depending on how the source release the energy. One event, it may release a mix of seismic wave of different frequency. The peak and the trench depends on the combination, the mixture of seismic wave that's coming from the source. So the pattern may not be exactly the same. Again, so what we think, there's several ways to do it. One way is do nothing, okay? Because the chance to happen is quite rare. The chance is low. Another way is to improve the structural system for the future building. We think that it's possible to make the structure more resistant to such a long period ground motion. I think I will not go into detail, but the idea is summarized in one keyword. We want ductile structure wall. Okay, structure wall. It is possible to design the reinforced concrete wall to be more deformable, more ductile. But in engineering, to do that, we should try to make sure that it will not fail in brittle mode. But there are many, we can have a long list of brittle failure mechanism. So in order to make the wall ductile, structural engineer will have to control, make sure that all this brittle mode will not happen. So they have to take care of all this detail. Make sure that it will not fail in shear, it will not fail by outplane instability, it will not crush. So all this can be done by the good engineering practice. In the past, we have that in the standard, but may not be that clear. But after this earthquake, I think we are going to focus more on this one and will improve further. After we have a ductile wall, then the structure can deform up to more than 2% roof drift. So when we come back to this one, the capacity of the structure will go above this level, not 0.6, 0.5, not 0.7, but 2%, if we can make the structure to become ductile. Okay, if we go with this measure, structure will be safe, you don't have to run out of the building, but your structure, your non-structural component may be damaged. Okay, your non-structural wall will have a crack, slight to moderate or severe. Your elevator may have problems. Your ceiling have a damage. Your water electrical system. Your buildings may not be functional. So even though the structure may be safe, you may not be able to use the buildings if it's hit by such severe earthquake again. Another way to handle this is to increase damping. Okay, because most buildings have damping low, in a low level, 1%. If you can increase to 2.5%, 5%, the curve go down. And when its curve go down, then the impact to non-structural component or the functionality of the building will be less. How to increase the damping? This is the last slide. We need to adopt this kind of measure. We call energy absorbing device. There are many types of this. We call this example is called viscous damper. We put something like hydraulic piston inside filled with viscous liquid. We install this kind of viscous damper inside the building. It will artificially increase the energy absorption ability of the structure. We have many different types: oil dampers, viscous damper, metallic damper. The technique used a lot in Japan, but have never been considered in Thailand. But after this event, maybe this is the first technology we may have to come back and look at it. If we want the structure or the buildings to be functional even after a severe earthquake in the future, maybe this is one attractive option to be considered. So I think that's all that I want to explain about what we learned from this earthquake event. Thank you very much for your kind attention. Thank you.